Okay, let me see if we can prove that the big number must consist. Sorry, what I thought you were going to do is what she did, and I still heard some. I got screwed up there. Oh, really? Well, if I screw up, you can fill in the blanks. As Wendy noted, all of these theorems have extensions to arbitrary metric spaces, but we're just interested, since we're doing integrals in the real line, we're just interested in a one-dimensional real version of these things. So the theorem we'd like to show is if K is compact and what should we call it? Open sets O, so alpha in A, say, is an open cover of K, then as a vague number. I.e., if S is a set, it's a subset of K, and the length of S, we're using absolute value bars here around sets. This could be an interval, this could be a couple of intervals, it's the total length of the set S. And if S is less than the delta, which is the Lebesgue number, then there exists a particular O alpha 0 such that S is completely contained in it. So that's what we're trying to show. This is an S, not another delta. So if I have, this is a closed and bounded set of reals. Let's just say for the orient this, that's the origin. This is a closed and bounded set of reals. So hence, by the Heine-Borel theorem, it's compact. So here's a cover. I'll note that that's a cover. That parenthesis is connected to that one. That parenthesis is connected to that one. Okay, there's a cover consisting of 6 open sets. I claim that there's a Lebesgue number such that if any set that's a subset of the original closed set S, S was this guy. Remember, this was S. All of ones in between. If I have a subset of S that doesn't have length greater than delta, it must be wholly inside a member of the cover. Well, I can't pick some points over here and some points over here because the length then would be from here to here, right? So I have to go on one side. I just showed S being split into 2 pieces, just for generality. So, you know, if you look at how the parentheses overlap, that distance there is about that much. That distance there is that much. This distance is this much. I would say that delta is probably going to be that distance there, from here to here, right? Because if I have a piece of the set S that is smaller than this little distance here, consider where it might be. If it's anywhere over here, it's either in this one. If it's sitting on this parenthesis here, it's still in the leftmost one. If it gets into no man's land here in the middle, right, it's still in that one. So you're good. You're good on this side. If you are a subset of S that's no bigger than that, you'll have to either be totally in this side or totally in that side. You're not so big that you span both, and nobody captures you alone, right? It takes two open sets to gang double team you, right? It's not necessary for the open sets to double team, if you will, prevent the football analogy in analysis. You don't need two open sets to double team a set smaller than that. A set bigger than that, though, you know, if I put a little subset of S there, right? You need both this open set and this open set to get him, right? But that's because he's bigger than the Lebesgue number for that color. So that's the model of the intuition behind it. So now let's try to prove why that always has to happen. Well, the first thing to do, I think, is to regularize the cover. Cover could be a bunch of weird open sets. You know, they could be sprinkled all over the place and in pieces. I think what we need to do is for each X in K, find the set O sub alpha X, which is in the cover and in which X resides. So all I've done is for every point in the set K, gone out and found an open set that contains one of the cover sets. Okay. Now, O alpha X is open, and X is contained inside. So what's the great property of open sets and basic open sets, which would be little connected open intervals? What about, can I always interpose one between O sub alpha X and X? You know, if I have an arbitrary open set, which can be something like that of real numbers, okay, and I go pick an X, is it always possible for me to get a connected open interval containing this point inside the open set that's given? Here's the open set that's given. That's the OAX.
That sounds like a constraint.
I can always do that, right? If that were, for example, like a half open set, and I picked a point here at the end, I couldn't do that, right? Or if it's a fully closed set, I couldn't do that either. I might be able to do it, you know, even if I had a fully closed set and I pick a point here, well, I can still do it. The thing about open sets is you can always do it. You can always interpose a basic open set, which is a connected interval, open interval, that contains the point of interest and is contained in the larger arbitrary open set. So what I'm doing here is sort of regularizing the collection of sets that I have to deal with. The OAXs can be all over the lot, you know, weird open sets. So we can find an interval. We'll make it a symmetric interval. What should we say? X minus epsilon X plus epsilon that's contained in O alpha X. Right? For each X. There's no doubt we can do it, right? So we've gone out, found the arbitrary open set containing X, and we've plunked down a very predictable knowable, basic, symmetric even, interval of total length 2 epsilon. Oops, we made a mistake. That's going to depend, the epsilon is going to depend on the x, isn't it? I mean, if our x is sort of toward the end of one of these open sets, epsilon x is going to have to be small. If he's dead in the middle, then we're going to be, we can be wasting